Okay, so in this video we're going to talk about optimization with geometry. Alright, so some optimization problems involve generating a function involving geometry. So in these problems, we're going to follow a general strategy. Part 1, we're going to define the variables. Part 2, we're going to write the optimization variable as a function of the other variables in the problem. Part 3, we're going to use relationships between the variables. Relationship between the variables to write this function, to make this function a function of one variable. And then part 4, we're going to differentiate this function to optimize. So we differentiate and find the zeros of the derivative to optimize this function. To optimize. Okay, so let's look at an example here. So we'll call this example 1. So let's say a business wants to fence an area adjacent to a building if they have 200 feet of fence. What dimensions will maximize the area? Okay, so let's define some variables. So let me draw a building. Here's a building here, 3D picture of a building here. And we have a fence adjacent to the building, something like this. And we want to maximize this area. We want to maximize the area enclosed. So first we'll introduce some variables. So we'll call this dimension, the distance out from the building, x, and we'll call the length of the fence parallel to the building, y. So our area, we'll call A, is going to be x times y. And then we have 200 feet of fence. So we'll have x plus y equals 200. That's a constraint. So x plus y equals 200, or 2x plus y equals 200. Okay, so we have our area as a function of x and y. So we've defined our variables, and we've written the optimization variable area in terms of the other variables, x and y. And now we want to use relationship between the variables to make this a function of one variable. So A is a function of x and y. We want A to be a function of just x or just y. So we'll use this constraint here. This is our constraint over here to write this area as a function of just x. So what we'll do is we'll solve for y by subtracting 2x from both sides. And then we'll put that into our area formula, and we'll get x times 200 minus 2x, or 200x minus 2x squared. And now this is a function of one variable, function of just x, and we can maximize this. We can maximize this using the derivative. Okay, so we'll take the derivative of this function. We'll get 200 minus 4x, set it equal to 0. We'll get 4x equals 200, or x equals 50. And if we have x is 50, then we can find y. Y is 200 minus 2 times 50, which is 200 minus 100, which is 100. So y is 100, and x is 50. We can see that these x and y values correspond to a maximum by graphing our area function. So if we graph our area function, it has zeros at 0 and 100. And it has a vertex at 50, and that corresponds to the max area. Okay, let's do another example. So at UPS, the length plus the girth of a box cannot exceed 60 inches. What box with square profile and satisfying requirement has the largest volume? Okay, so let me start by drawing a box with a square profile, and then let me explain what girth is. So girth is the distance around the box. So this is girth here, girth. So the girth plus the length is this dimension. Girth plus the length can't be greater than 60 inches. Okay, so let's introduce some variables. We'll call the length y. So this is y. And then we'll call the width and the height x. It has a square profile, so these dimensions are going to be the same. Put x over here. And so now we can set up our constraint. So the constraint is going to be length plus girth is less than or equal to 60 inches. We're going to try to maximize our volume, so we're going to make that equal to 60 inches. The length is y, and the girth is the distance around the square. So it's going to be 4 sides around the square, 4x. So our constraint is y plus 4x equals 60. And then we want to maximize the volume. We want to maximize the volume of this. And the volume of a prism like this is the height times the width times the length. So x times y, or x squared y. Okay, we want this v. We want v as a function of just one variable. So what we need to do is use our constraint to rewrite v as a function of one variable. So if I take my constraint and I solve for y, I'll get y equals 60 minus 4x. And if I put that into my v, I'll get v equals x squared y, or x squared times 60 minus 4x. And we'll get v equals 60x squared minus 4x cubed. Okay, so this is good. This is a function of one variable. Now we can use the derivative to to find what x value maximizes this function. So if I take the derivative, I get 120x minus 12x squared. Set that equal to 0. Let's pull out the GCD. We'll get 12x times 10 equals 120, and 12x times x equals 12x squared. So we'll get 12x times 10 minus x equals 0. There's two zeros here, x equals 0, and 10x minus x equals 0, or x equals 10. If x equals 0, the volume is going to be 0. That's definitely not right. So we'll cross that one out. And if x equals 10, we'll get y equals 60 minus 4 times 10, which is 20. So we'll get a box that looks like this, 10 by 10 by 20. And this is the largest volume box. Now we can see this graphically if we graph this function v. If we graph this function v, it's going to look like this. And the maximum is indeed at 10. All right, I hope you found this video useful.